opportunity to talk about Ricci soliton. And people say the best way to learn something is to teach. So actually, I'm learning something. It took a long time to choose the topic I will talk, because there are many things I can choose. So finally I decided I will start with some beginning, and the purpose of this mini course, I will give a almost complete proof to this theorem of so I will. It's a lot of people. Cao, Chen, Zhou, finally, and actually before that there are Perman and Lee Wallace. And Peterson, and somebody else. Finally, the proof, the result is that all non-compact, complete, three-dimensional gradient soliton shrink soliton. Must be S2 cross R. So actually, the result first proved by Perman. He needs non-collapsing, bounded curvature, and a non-negative curvature. So after several years, the condition can be all the conditions can be removed, and the proof, the idea of the proof, part of the proof can be generalized to higher dimensional case. So I think the tools used in the proof of this theorem may be it's very important. It involves many basic tools in geometric analysis. So first I will give some basic definitions, and I think I will prove some basic lemmas. I'm now inviting all the people to join me to sometime to help me to give the proof more clearer. So the definition, I will call it 1.1, is that M, G, V is a Ricci soliton of course, where M is a manifold, G is a metric, V is a vector field. If the Ricci curvature plus J equals to rho G I J, or we can write down as Ricci plus V G equals to rho G. So this is it's a definition of Ricci soliton. Of course, it's a generalization of Einstein metric when V is 0. If V is 0, this is equivalent to, or rho is a constant. Rho is a constant. Rich is to, that means Einstein. So the Ricci soliton is a generalization of Einstein metric. Or this manifold is more general than Einstein manifolds. So when V is the gradient of a function, we called we write down as it's called gradient Ricci soliton. So actually, this is the most important special case for Ricci solitons. So before I give some examples, I will prove some basic results about the Ricci soliton. The first one is lemma 1. It's due to Hamilton. I will fix the notation here because I will use it frequently. So my metric is defined like minus my curvature is y. And the curvature tensor is defined x, y, z, w. So I also would like to record some definitions. For example, I will need this kind of thing. So in this kind of notation, we have for orthonormal base. So the Hamilton proved that for the Ricci soliton, be a gradient then the scalar curvature plus gradient f squared minus rho f equals to constant. So here we called this lim f is called potential function. Potential. So the potential function and the scalar curvature have this this relation. The proof is like this. First, we have we need to prove this is constant. We need to prove that the derivative of this function is 0. So we first need the following. So we need to prove that the derivative of this kind of thing. So we need the first from branch entity, we have m plus rm, okay, j, m, okay, is equals 0. So we just let I equal k. We have, so I equal k. We have reach. So I still use this kind of notation for reach m plus j I equal k. So we have here r k j m k plus r and j equal k. This I equal k is minus reach curvature, because we just change this jm equals to 0. So if we take j equal to r, we have gradient m r j equal to r, and take sum, and we have here j equal to r. This is minus. You just change the term. We have minus r j equal r k m k minus j equal to r, which is j m j. We have the convention that the repeated index takes sums. So this equals this. So we have reach twice. Right? So we just take a derivative of this equation. We have gradient m r, and this is the sum of fi. We take m here, and we have we need to compute this. This is square. So this one is equal to j n j, and this we have. That's just to check my notation. Okay, that's right. Just to make sure. So if this is twice, if sometimes I omit here. And plus so I will take reach. This I will use this equation because we have the Ricci soliton, we have Ricci Jm, Ricci Ij plus Fij equals rho G Ig. From this equation, we substituted the Fij to here, and then this one goes to Jm here. So we need to compute this. So R Jm J equals to, in general, it's take a general case. We have R J equals to because so if this is a matrix, so it's there. So we also have Jm so Ij is permanent. So it's equal to this. So if you let I equal to m, so Jmj is equal to, just take I'm a little bit use a bad notation here. So this is m. Take 1, 2, 3, and 1, 2, 3 is permit this one. So I will take j m plus the first equal to third. So the first equal to third, I equal to, so R it's better for you to see better. I would like change a little bit here. So just use this notation is better. J M J. It's okay. I think you can understand this. So I J. So M. FR. So this is the Ricci curvature. So I just call this M. So this is Laplace because it implies R plus Laplace F equals to N rho. So this equals to this is equal to R so complicated. this is a reach. I get a little bit confused here. It's so complicated. J here. Oh, I don't need this one. I need this one. Actually, I don't need this computation. Sorry. I have IJM plus IJ equals to so I need just perturbate it. This one goes. I will change. Okay, this is JK, RJK, I just change the this equal this. So this equals to, this is RM, it's RMJK, it's MJK here, it's IJK, MIJ. So we have gradient. This is gradient is, take some here. So we have so this equals to and so we have, I forgot about it. In the beginning, I take some wrong notations here. So I have R plus gradient F squared plus F equals to IJ plus Fj rho Gij F J. So this is exactly the equation. So it's 0. So actually, I have used several equations here. I will put here because we will use very often this kind of thing. And we have constant. So from this we can prove the proposition. Point 1 is due to Hamilton. And the EV. Or compact steady or expanding. So now I will define here if rho is positive, we call it shrinking, and rho equal to 0, we call it steady, and rho negative, we call it expanding. So the Hamilton and Eve proved that all compact, steady, or expanding soliton, gradient soliton, must be Einstein. So that means when the compact, the steady and expanding soliton are trivial ones. When it is Einstein, we call it trivial. So the proof is quite, it's equivalent to prove that the F is constant. So to prove that it's constant, we will use the two equations here. It's a simple application of maximum principle. So we just assume that. First we assume rho is negative. We take a point. Is this fx equals to maximum x em. So we have, at this point we have gradient f. This point is 0, and Laplace this point is positive. No negative. No positive. Because it's a maximum point. So we have Rx0 equals to we have so if we use these two equations, we have we have R here. We also have R here. So we just minus this equation by this equation. So we have Laplace F minus Laplace F minus gradient f squared and plus 2 and rho so this is a constant. So we have rho f x0 equals to rho on this side. So this is 0. This is less than or equal to 0. It's bigger than or equal to rho minus c. So the f x0 less than or equals to n then minus. We can do the same thing for the minimum point. So we know that the maximum point is less than or equal to this. So if we would do it, so if we take x bar, it's a minimum point, f x bar equals to minimum x equals. So we can see that we still have this equal to 0, and it's bigger than or equal to 0. So we have this, the relation that the same is bigger than or equal to c. So that means minimum point is bigger than or equal to maximum point. This implies f is constant. So if it's constant, means that it's Einstein. So now I will give some examples. Examples of non-trivial ones. So all the Einstein manifolds, are solitons. So on when the soliton is Einstein, we call it it's trivial. So also, if you take a product of two Einstein manifold, it's still Einstein. So also trivial ones. So for example, you have spheres, a hyperbolic space, or a trivial ones. The example one I will take is Rn. So, but I will this is, of course, if you take f equals 0, it's a trivial one. But it is special if you take standard metric. You take a function f here. You have first you have, if you take f equals to 1 over 4 x squared, you have Ricci, which is 0, plus f Hessian of f. So you have is equals to g. So you have this one. So it is a shrink soliton. So if this one, if you take minus, so you have Ricci plus d squared f equals to minus. So again, this is an expanding soliton. So this is a very special example. If you take a different f, the metric can be both. Sometimes it can be shrinking, sometimes it can be expanding. Of course, if you take f as a linear function, the Hessian of f is 0, so it is a static soliton. So if f is as a linear function, if take just function mg is a static soliton. This is an important example. Also, I would like to mention that the S2 cross R is also a shrink soliton. If you take S2 cross R, if you take the product metric SR cross R metric, the product metric, I think it's take G S2 cross the G. If I take a F, if I call this T, I can take T 4 over square. Just take it is a now I have to take the 4. The metric. I just take the metric. Metric should be which constant? I take super constant, so such that or one. I'm a little bit confused. The F is equal to this, so it's a shrinking soliton. You can have a constant here. It's a shrinking soliton. So it is also an example. So, but by the way, I will prove that maybe in the second lecture. I will prove that this one cannot be a shrink soliton. It's naturally asked why you begin with S2, not S1. Cannot be a shrinking soliton. Now I don't repeat the Ricci here because every time we say about soliton, it means Ricci soliton. When we principally after that, I will deal with the gradient soliton. So sometimes I don't speak as gradient soliton, but it means gradient soliton. So I will not have time to go to in detail some more examples. For example, actually we have compact examples on CP2 with connect sum with the minus CP2. This means you change the orientation of this. There is solitons. metric solitons, shrinking metrics. Of course, shrinking because compact is a shrinking metric. This example was done by Detang Zhou and Koizu first, and Zhou. Also, after that, on the compact toric Kelly manifold, there are soliton structures. -2, you have 2 pull-up points. This is due to 1 and 2. So the construction of this kind of matrix is quite natural, because you take a point out here, then you construct a symmetric matrix to connect to two manifolds, and you just fix the solution. You can find the metric, which is and then the function which is a shrinking soliton. So according to the proposition of Hamilton and Ewing, the compact case, if the most interesting things, maybe a more complicated cases are non-compact cases. So especially for steady and expanding case, I didn't prove that for steady case, but it's similar. So I will leave it to exercise. Also the same idea. So the important thing, example of example 3 is SIGA. That is due to Hamilton in two-dimensional case, R2, you have a metric. You have F. The metric is G equals to dx squared plus d squared over 1. So it looks like this. It has almost a linear volume growth, and the curvature goes to 0. And actually, the curvature is positive on this manifold. You had a positive Gauss curvature, and also Hamilton classified the two-dimensional case. Brilliant salt. Brilliant salt is on if you take a metric, which is rather symmetric, and you can take a function also only depend on R. So you can write down the Ricci curvature, and you can write down the Hessian. So Robert Bryant solved the system of ODE equations and prove that there exists this kind of metric and the function which makes the manifold a steady soliton. It's a steady soliton. Exists. Soliton. With metric, with rotational symmetric metric. The techniques used by Koizu and Huaidong Cao also can be generalized to non-compact case. You just blow up some point, and then you construct a U1 symmetric metric, so that you have non-compact shrink solitons like this. So. The solitons are important if you, in the viewpoint of Ricci flow. Now I will explain. Well, actually, the Ricci solitons are special solutions for Ricci flow. So this kind of solution we call as self-similar. The definition of self-similar is. To Ricci flow. If that means if there exists a function to and one parameter family of diffeomorphism. Phi t such that g of t equals to sigma t g 0. Is the solution to Ricci flow. That means if there is a function and a family of diffeomorphisms such that the metric, this metric is the solution of Ricci flow, then we call GT is called self-similar solution to Ricci flow. So if you take this set called G Riemann metric. This is a space of Riemann metric on M. If you take this defined as all diffeomorphisms, from M to M. And you take R, C, non-negative positive numbers, which act M metric as this. You have G, and then actually for the Ricci flow we care about the metric. The matrix up to diffeomorphism and a scaling invariant. So if you take Ricci flow is it's a flow on the Ricci flow can be considered as a flow on this space. So if you take the quotient of diffeomorphism plus R, so this kind of the self-similar solution is just the fixed point of Ricci flow. In this sense, if you take this space, so the self-similar solution is exactly the fixed point if you take the Ricci flow in this space. So why the self-similar solution is exactly the Ricci solitons? So we just need to do a little bit of computation here, and we see that it is exactly. So we just take differential. We call this equation here. We have G naught T equals to phi star T G0 plus G0. So where is where x is the vector field given by phi of t. That means x phi of t p equals to p t. Since you have this is the derivative, so you have relationship of the metric, Ricci metric is invariant. Ricci G naught. So we know that the G is the solution of Ricci flow. So this one equals to twice minus 2 Ricci t equals to sigma of t first we have this one equals to G naught t. So this equals to this side. So we have this one equals to so you have the phi star here, phi star here, phi star here. We have twice Ricci G of 0 equals to sigma t G. So there are two cases. If identical to 0, so that means sigma t equals to some 1 plus, there is a positive number such that this equal to this one. You can normalize because you have sigma 0. You have G0 equal to this. We can prove that sigma t there is epsilon, such that sigma of t equals to 1 plus epsilon t. So in this case, you just put it in. You find that this is constant. This when so you just take phi this is it becomes a soliton. This is constant. This is constant for when t is equal to 0. So for each fixed t, this is a soliton. So if the case 2, if there exists t0 such that different to 0, we can construct explicitly a vector field y of t to satisfy actually such that equals to x y vector field equals to that means this is a stated case. We just we use the x and we can find a y using this point. We can find a static soliton in this case. That means in this case it's a static soliton. In this case, this case is shrinking or expanding. Okay, this is more or less the basic material. So now I will move to shrink soliton. So first I will prove a very recent result to prove that this theorem is due to Bing-Long chain. That let MGF be a gradient shrink soliton all of these are complete. So I complete, non-compact. Not this. Then the scalar curvature is non-active. So before I go get into the proof, I will write down some basic formulas for Ricci flow, because so I will not write all of that. First I will write down the one I need. So if the metric is T of t, this. So you have scalar curvature equals to each, right? And so so if you have soliton, you have Ricci plus now we have shrink soliton, we have rho. So because there is a more or less standard computation using the Ricci flow, you have you have Laplace R equals to twice rho R minus so it's important to remember that when you have a Ricci soliton, it is a solution of Ricci flow. So every time you want to get information for the Ricci soliton, it's very useful to go back to the flow and using the property. Actually, for example, the scalar curvature satisfies this parabolic equation. So when you want to prove that R is non-active, you need to use this equation to prove that R is non-active. So when M is compact, we just use this equation. You use maximum principle. It's not very easy, but it's a good exercise to prove that R is non-active. So it is different from that one. So I will prove that this theorem directly for non-compact case. So it is an example for us to learn how to prove this kind of result. Actually, Pinluchen proved this for ancient flow, because the shrink soliton is the ancient solution for Ricci flow. That means that GT exists for minus infinite to some fixed point here. So suppose Gij of t is a solution to Ricci flow on t, where t is positive. I will not have enough time to prove it. Instead of that, I will first prove a comparison theorem for the proof. So net d t be a distant function with respect to GT. So we have known that this equal to this. So we will use this distant function. We need a similar relation. We claim that, actually not we claim, it's a pairman. Prove that the estimate for this if Ricci is bounded by on we have a comparison theorem for distant function for flow. So I will prove this claim, then I will leave the proof of this theorem for the next time. So actually, this is it's a. So we can take this x0. We can take a geodesic gamma to x. We just denote L. Because now the 2 points are fixed. So the gamma is the geodesic. And we suppose that it is normalized with GT. It's a normalized geodesic. So we can take this is E1. This is x here. The x equals to gamma prime, the vector field of this geodesic, and we can take E1, En plus 1, parallel vector field. So we have Laplace dt x0 x equals to sum. We can take I equal to 1 index. Where xi are Jacobi fields along the geodesic, and with xi of R equal 0, and xi of R equals to EI R, where I. So the Laplacian equal to this. So because we can assume this geodesic is minimized, it's shortest geodesic. So from the Morse theory, the index should be less than 4. So the index xi is less than or equal to ny. If you take where yi equals to zero, whereas and to here. So by a direct computation, we have less than or equals to the sum of we just put it in curvature. Yes. So this part is Ricci curvature. And this part we can use this information. We have 1 over r squared m plus 1 minus s squared Ricci curvature and plus so we know that Ricci curvature is bounded by this number. So we can this can be computed. So we have m plus 1 r0 minus because it's less than or equal to, we can put it positive because this is bounded by a number. So r squared. So this r0 m plus 1 square. This bounded by I0 square. So we have 0 r0 s square. Yes. So we can put some constant here. Actually, we can put somewhere to complete this kind of thing. Minus. We can complete from here. Yes. So this can be computed. And this one, we will see that so we know that the dt x0 x equals to integral of L gt xs gamma plane. For us, it's the same thing. Dx here. So if you compute the derivative, it's equals to so if if we use in the Ricci flow, because we use the Ricci flow and we use the gamma prime is a unit vector, so it equals to minus Ricci, because there is a half here, so it's cancelled, so it equals to ds. So when you combine this with this, it cancels this term, and this term is controlled exactly by that number. So so we have this equation, this property, and we can combine with this equation, and we use cutoff function. We can prove this theorem. I will leave it in the next lecture. Okay.